Now let us discuss about VI characteristics of PN junction. So VI characteristics is the curve between voltage across the junction and the circuit current. So usually voltage taken along x-axis and current along y-axis. This is the circuit arrangement for determining the VI characteristics of a PN junction. So the characteristics can be studied with zero external voltage, with forward bias, and with reverse bias. First one is zero external voltage. So this is the circuit arrangement to study the VI characteristics. Here is the PN junction. This is milliammeter. This is voltmeter. This is variable resistance. This is key. This is supply voltage. So first one is zero external voltage. When the external voltage is zero, that is the circuit is open at key, the potential barrier at the junction does not permit current flow. Therefore, the circuit current is zero, as indicated by the point O. Next one, with forward bias. With forward bias to PN junction, P-type connected to positive terminal of battery and N-type connected to negative terminal. So the potential barrier is reduced. At some forward voltage, that is for 0.7 volt for silicon and 0.3 volt for germanium, the potential barrier is altogether eliminated and current starts flowing in the circuit. From now onwards, the current increases with the increase in forward voltage. Thus, a rising curve OB is obtained with forward bias. Now look at the region OA. The current increases very slowly and the curve is non-linear. It is due to the external applied voltage is used up in overcoming the potential barrier. However, once the external voltage exceeds the potential barrier voltage, the PN junction behaves like an ordinary conductor. Therefore, the current rises very sharply with increase in external voltage, which is shown with the region AB. With reverse bias to the PN junction, that is P-type connected to negative terminal and N-type connected to positive terminal. Potential barrier at the junction is increased. Therefore, the junction resistance becomes very high and practically no current flows through the circuit. However, in practice, a very small current, that is the order of microampere, flows in the circuit with reverse bias. This is called reverse saturation current and is due to the minority charge carriers. It may be recalled that there are a few free electrons in P-type material and a few holes in N-type material. These undesirable free electrons in P-type and holes in N-type are called minority charge carriers or minority carriers. To those minority carriers, the applied reverse bias appear as forward bias. Therefore, a small current flows in the reverse direction. If reverse voltage is increased continuously, the kinetic energy of electrons, that is the minority charge carriers, may become high enough to knock out electrons from the semiconductor atoms. At this stage, breakdown of the junction occurs, characterized by a sudden rise of reverse current and a sudden fall of the resistance of barrier region. This may destroy the junction permanently. Remember one thing, the forward current through a PN junction is due to the majority carriers produced by the impurity. However, the reverse current is due to the minority carriers produced due to breaking of some covalent bonds at room temperature. Now let us discuss about some important terms. First one is breakdown voltage. It is the minimum reverse voltage at which the PN junction breaks down with sudden rise in the reverse current. Under normal reverse voltage, a very little reverse current flows through the PN junction. However, if the reverse voltage attains a high value, the junction may break down with sudden rise in reverse current. Now let us discuss it clearly. Even at room temperature, some whole electron pairs are produced in the depletion layer, as shown here. With reverse bias, the electrons move towards the positive terminal of the supply. At large reverse voltage, these electrons acquire high enough velocities to dislodge valence electrons from semiconductor atoms, as shown here. The newly liberated electrons in turn free other valence electrons. In this way, we get an avalanche of free electrons. Therefore, the PN junction conducts a very large reverse current. Once the breakdown voltage is reached, the high reverse current may damage the junction. Therefore, care should be taken that reverse voltage across the PN junction is always less than the breakdown voltage. Next important term is knee voltage. It is the forward voltage at which the current through the junction starts to increase rapidly. When a diode is forward biased, it conducts current very slowly until we overcome the potential barrier. For silicon PN junction, potential barrier is 0.7 volt, whereas it is 0.3 volt for germanium junction. Once the applied forward voltage exceeds the knee voltage, the current starts increasing rapidly. In order to get useful current through a PN junction, the applied voltage must be more than the knee voltage. Remember this one. The potential barrier voltage is also known as turn-on voltage. This is obtained by taking the straight line portion of the forward characteristics and extending it back to the horizontal axis. Now let us discuss about some limitations in the operating conditions of PN junction. Every PN junction has limiting values of maximum forward current, peak inverse voltage, and maximum power rating. Now let us discuss them one by one. First one is maximum forward current. It is the highest instantaneous forward current that a PN junction can conduct without damage to the junction. Manufacturer's datasheet usually specifies this rating. If the forward current in a PN junction is more than this rating, the junction will be destroyed due to overheating. Next one is peak inverse voltage. It is the maximum reverse voltage that can be applied to the PN junction without damage the junction. If the reverse voltage across the junction exceeds its peak inverse voltage, the junction may be destroyed due to excessive heat. The peak inverse voltage is of particular importance in rectifier service. A PN junction, that is a crystal diode, is used as a rectifier to change alternating current into direct current. We will discuss in next video this one. In such applications, care should be taken that reverse voltage across the diode during negative half cycle of AC does not exceed the peak inverse voltage of diode. Next one is maximum power rating. It is the maximum power that can be dissipated at the junction without damaging it. The power dissipated at the junction is equal to the product of junction current and the voltage across the junction. This is a very important consideration and is invariably specified by the manufacturer in the datasheet.